How exactly did Earth get its moon? And what if that same cosmic event also helped kickstart life on our planet? We're about to dive into some fascinating theories about how both our moon and life itself came to be. It might seem like a strange question to ask. After all, the moon has always been a constant presence in our sky, so it was a long time before scientists seriously began to wonder, where did we get that thing? And what a thing it is. The moon is truly unique. Just look at the other planets similar to Earth. There are only 4 of them: Earth itself, Mars, Venus, and Mercury. Venus and Mercury have no moons at all. Mars has 2 tiny companions, Phobos and Deimos, which are so small they're barely there. But Earth has this enormous moon. In terms of size, it's not that much smaller than our own planet, less than 4 times smaller in diameter. In terms of mass, Earth is about 81 times heavier. So, satellite doesn't quite do it justice, it's more like a second smaller planet. Astronomers often refer to the Earth-Moon system as a double planet, much like Pluto and its large moon Charon, which is undeniably a double planet system. Charon is only 8 times less massive and half the size of Pluto. Our moon is a bit smaller in comparison, but the mystery of its formation still keeps scientists on their toes, leading to several competing theories. At least 3 theories are in constant discussion. First, the moon could have been an independent planet that, after a chance encounter, was captured by Earth's gravity and has remained here ever since. That's one possibility. A second idea is that the moon could have formed alongside Earth, from the same primordial cloud of material that created our solar system, but as a separate body. That's another viable option. But a third scenario, which emerged much later, is now considered the front-runner. When the first samples of lunar regolith were brought to Earth by American Apollo astronauts, the initial chemical analyses astonished researchers. The lunar soil was remarkably similar to Earth's own mantle, the upper layer of our planet. Below this rocky mantle, Earth has an iron-nickel core. This similarity was so striking that it gave rise to the idea that a catastrophic event had split Earth's material into 2 pieces, what remained as Earth and what became the moon. How could that happen to an already formed planet? Only through a cataclysmic disaster. This led to the elegant hypothesis of a colossal impact, another planet striking the young Earth. This now vanished planet was named Theia, a fitting choice from Greek mythology, where Theia was the mother of the moon and the sun. The sun isn't part of this story, of course, but as the mother of the moon, Theia fits perfectly. The theory goes that a glancing blow from the smaller planet Theia into the larger proto-Earth ejected a massive amount of material from Earth's mantle into orbit. This debris would have formed a ring similar to what we see around Saturn today. Over time, larger and larger clumps formed within this ring, eventually coalescing into one large body, the future moon. Its gravity then swept the area clean of the remaining construction debris. Today there's nothing else in the moon's orbit. It either absorbed everything or gravitationally flung it away into the solar system. It's a beautiful idea, and it's backed by computational models. Mathematical simulations of Earth and a planet Theia, roughly the size of modern-day Mars, about 1/10 of Earth's mass, showed that a grazing tangential impact could indeed blast a significant amount of material into orbit. While most of this material would fall back to Earth, a fraction would remain as a disk, which would then form the moon. Physics and mechanics seemed to validate the hypothesis, and for a long time, it was the leading explanation found in most textbooks. But as time went on, and new lunar samples were brought back by Soviet and more recently, Chinese missions, our analytical capabilities improved dramatically. We can now analyze not just the chemical composition, but the isotopic signature of individual elements. It turns out that the isotopic composition of oxygen, for example, which has 3 stable isotopes, O16, O17, and O18, is a powerful marker of a substance's origin. And what did we find? The isotopic signature of lunar material is virtually indistinguishable from that of Earth's crust. This is astounding because the impacting body, Theia, which would have formed in a different part of the solar system, couldn't possibly have had the exact same composition as Earth. This casts serious doubt on the classic Theia hypothesis. In response, modified versions of the theory have emerged. Recently, scientists from a geophysics lab at a leading European university proposed a new twist. What if Theia wasn't a fully formed planet, but rather the dense iron-nickel core of a small planet? A metallic projectile about 1,000 kilometers in diameter, similar to the dwarf planet Ceres. According to recent research from the University of Göttingen, this cannonball could have slammed into Earth, passed through the mantle without shattering, and merged with our planet's core. This would mean the moon is made almost purely of terrestrial mantle material ejected by the impact, neatly explaining the identical isotopic signatures. Other models explore what Theia might have brought to Earth. The origin of our oceans, for instance, is still debated. A mega-impact would have heated Earth so intensely that any existing water should have boiled off into space, leaving a dry planet. Perhaps then, Theia delivered new volatile compounds, like carbon. This idea is being intensely modeled now. A carbon-rich body formed far from Earth near Jupiter could have been flung inward by the gas giant's gravity, struck Earth, helped create the moon, and seeded our world with the carbon essential for the emergence of life. In this version of the story, life itself may have the mega-impact to thank. However, some scientists, like the prominent physicist Dr. Andrei Volkov, argue that a single mega-impact couldn't have happened. His reasoning centers on water. We used to think the moon was completely dry. After all, if its material was atomized into a vacuum and orbited Earth for some time, any water vapor should have escaped. And for a long time, that was the prevailing view. But then, instruments on various international probes detected significant amounts of water-bearing minerals in the moon's surface layer. At first, this was explained as acquired water, created when protons from the solar wind hit the lunar surface, broke apart oxygen-bearing minerals, and formed water molecules. But recent analyses, including those of samples from China's Chang'e 5 mission, have found zircon crystals containing water that could only have formed deep within the moon. This suggests water is part of the moon's internal structure. Dr. Volkov contends that a single violent mega-impact would not have resulted in a moon with so much internal water. So what could have? He proposes a multiple impact scenario. Instead of one giant collision, the early Earth was bombarded by a series of smaller yet still massive bodies. Each of these impacts would have been less cataclysmic, heating the planet and the ejected debris less intensely. This would allow chunks of Earth's mantle containing their original water to be launched into orbit without being completely vaporized, eventually coalescing to form the water-rich moon we are now discovering. Dr. Volkov's theory carefully balances celestial mechanics and geophysics, solving the tricky problem of getting debris into a stable orbit instead of having it fall back to Earth or escape into space. So now we have two competing impact-based origins, the single mega-impact or the multi-impact. So what's next? Well, we eagerly await pristine samples from deep within the moon. Up to now, we've really only scratched the surface. We need to either drill deep, which is honestly a pretty costly endeavor, or explore those lunar caves whose entrances we've already spotted in orbital photographs. NASA's Artemis program, aiming to establish a long-term human presence on the moon, has identified exploring these lava tubes and permanently shadowed craters as a key objective. These subterranean passages could lead us to primordial lunar material, untainted by solar wind and cosmic radiation, which might hold the final clues. Piecing together the solar system's 4.5 billion year history is no easy task, but as you can see, we're deciphering it step by step. And exploring these lunar caves could lead to even more stunning discoveries, potentially in the search for life. Who says the moon is a dead world? The surface is inhospitable due to radiation, but just a few meters underground, especially in caves, that radiation is blocked. There, we might find not only carbon-based compounds and water ice which we now know exists, but perhaps even signs of life. Understanding this could also clarify the origin of life on Earth. In the early days of our two neighboring worlds, meteorite bombardment was intense. Many biologists now see this bombardment as the very trigger for life's development. Although Earth is a geologically active planet, with rain, wind, and tectonic plate movement erasing ancient impact craters, we know these events happen constantly. The very existence of life might be the last remaining evidence of that ancient bombardment. We find the building blocks of life like amino acids inside meteorites. Each impact creates a temporary high-temperature chemical reactor, accelerating the chemical reactions that could lead to life. Exploring this process on worlds like Mars and the Moon, which have preserved their ancient surfaces, is crucial. Even Mercury, once thought to be lifeless, now seems more promising, with stable temperatures and potential for life deep beneath its cratered crust. Ultimately, the Moon, Earth, and their terrestrial neighbors are all connected by a shared history of cosmic collisions. These impacts didn't just shape their appearance, they may have defined the conditions in their interiors and, just maybe, sparked the development of life itself. To make sure you don't miss our next journey into the cosmos, please subscribe to the channel and give this video a thumbs up.